So in chapter 10 of your textbook authors begin talking about the different properties and principles of a probability-based sample. And as you probably have gathered from these lectures, probability-based samples really are a lot more useful to us as researchers, and they're a lot more interesting to us. And they have a lot of properties that can be extremely handy to have in a study, provided that you understand how they work. And so one of the things that they've done is they've put together what they call 8 sample size and accuracy axioms, just about the properties of what a probability-based sample looks like. So I'm going to take you through each of those really quickly because I think that they're pretty important. So first of all, the only perfectly accurate sample is a census. So if you're going to conduct a sample of a population and you want perfect accuracy, the only way to get there is to conduct a census. There's just no other way. And most of the time, it's not cost effective or even remotely feasible for us to conduct a census on a study. So we cannot always shoot for perfect accuracy. We can rarely shoot for perfect accuracy. So we need to accept that when we're dealing with samples that are probability based. 2, a random sample will always have some inaccuracy, which we're going to call the margin of sample error or just sample error. Those are both acceptable terms for it. Now this is usually going to be expressed in plus or minus terms in a percent, like the president has an approval rating of 43% plus or minus 3%. That would be how we express that margin of sample error. 3, the larger a random sample is, the more accurate it is, meaning the less margin of sample error it has. And this is an important point to understand, that if we want accuracy, we have to increase sample size. Because what that means is that the larger our sample size is, the less error we're going to have associated with the way that we sampled. So if we want to be able to say the president has a 43% approval rating plus or minus 2%, the only way we can get there to get that plus or minus 2% instead of 3% is to increase the sample size. And that's because, point 4, margin of sample error can be calculated with a simple formula and expressed as a plus or minus percentage number. Now again, these axioms, we're talking about a random sample, a probability-based sample. In other words, we're not talking about convenience samples or non-probability samples where the researcher believes that the findings approximate reality, although, I'm just going to tell you, researchers do it all the time, where they take a non-random sample and then they put plus or minus on it. And they just say, well, you know, we know that it's not random, but if it were random, this is what the margin of error would be. And that's a cheat, but we do it all the time in the research industry. We kind of have our little mea culpa, as we call it, about the fact that it's not appropriate to do, but you know what, we're going to do it anyway. So I just want to specify, margin of sample error is only about a randomly derived probability sample, not a non-random, non-probability sample. 5, you can take any finding in the survey, replicate the survey with a random sample of the same size, and be very likely to find the same finding within the plus or minus range of the original sample's findings. So what this means, this is what we call the confidence level. And what this means is that if you conduct a survey using a random selection process in your sample, you should be able to repeat that survey over and over and over and get the same findings that you got the first time. And what measures your ability to do that is what's called the confidence level. And we'll talk about the confidence level in another lecture in this series, but the idea is that if you are doing things properly, you should be able to get repeatable results by using the same technique. And by the way, when you're sampling, your random samples are always going to involve different people, right? So if you're sampling 500 people from a population of 100,000, every time you draw a sample, it's very likely that the people you're going to be talking to are entirely different from the previous sample if you drew them randomly. But you should still get the same results in terms of the statistics that you're drawing once the margin of error has been factored in. Which is one of the cool things about doing this kind of research, is that you should be able to get repeatable results that you can find over and over, and that helps you to identify trends and things like that. 6. In almost all cases, the margin of sample error of a random sample is independent of the size of the population. So the size of the population doesn't tell you how much error you're going to have in your statistics. It's the size of the sample. So if you have a population of 1,000 people and you take a sample of 30 people, you're going to have the same margin of error for the most part that you would have if you had a population of 10,000 people. So the size of the sample is what governs your margin of error, not the size of the population. A random sample size can be a tiny percent of the population size and still have a small margin of sample error. And we'll talk about this in another lecture in the series as well, but you don't have to interview that many people in a large population to get good results. Usually it's in the hundreds or low thousands. You don't have to interview many more than that to get good results. Again, this is like taking a sample of blood from your body for tests. You only need a little bit of blood to provide projectable results about what's going on through the entirety of your body. You don't have to pump all your blood out and then pump it back in, or you don't have to pump most of your blood out even, just a tiny little bit. So particularly with large populations, we don't need large samples. What we do need is we need sufficiently sized samples to reduce our margin of error to a point that we can trust the results. The size of a random sample depends on the client's desired accuracy, which is the acceptable margin of sample error, balanced against the cost of data collection for the sample size. So in other words, when a client is just trying to decide how many people they want to interview in a study, they really ultimately have to decide based on the cost of that study and what they can afford. There are times where a client would really like to have a high degree of accuracy, which means a low degree of error, but they're just not willing to pony up for what's required to get there. So they have to make a compromise in terms of what they're comfortable with in terms of accuracy, combined with what their budget can afford. One other point that I want to make, I believe it was made somewhere on one of these slides, but I just want to make sure that I state it explicitly, is that in a randomly derived sample, a small sample and a large sample are equally representative of the population, but they're going to have different levels of error. Okay, so if I am interviewing SIUe students and I interview 1,200 of them, I'm going to have data that are as representative as if I only interviewed 30 students. But because of error, my statistics in that size 30 sample are going to be much less reliable than the statistics in my size 1,200 sample. So they're both equally representative because they were randomly selected, so they're equally representative, but one has a much sharper resolution than the other. And that's a really important point to remember as well, is that sample size isn't talking about representation. What it's talking about is the accuracy, the amount of error that's associated with our findings. And we're going to talk about error a lot more in lecture series 7, as I've alluded to many times. So if the term's going over your head right now, don't worry about it. Just understand that ultimately, increasing the sample size helps us to reduce error, and that's a good thing.